Hello, in this video we are going to solve one trigonometric integral, at least one type of trigonometric integral. There can be many changes in these integrals, but we are going to focus on one. Let's see. So, what is the objective? Solving trigonometric integrals. The specific type we are going to see here is when the function is odd in sign. We will apply a change of variable, and this integral, trigonometric integral, will become a rational or irrational integral, depending on the exercise we are dealing. But normally in a rational integral. With this change, this is a very specific change for a specific type, but it's very helpful. Many times when you apply this change, it simplifies perfectly the integral. Sorry. What do we need? Some notions of integration and derivatives, calculus, and simplifying mathematical expressions. So let's see. What is the type of integral we are going to solve here? Let's see an example. Sine cube, cosine cube. A product of two trigonometric functions. Perfect. The power is 3. In this case, the function is, let me see, it's odd in sine. It's also odd in cosine. I'm not going to use that. And it's also even in sine and cosine. How do we know that? Normally because of the exponents of the function. Remember that a function is odd in sine if we change sine of x by negative sine of x, and the negative can be taken out from the function, can be just separated. It's a not easy idea. It's not an easy idea. But if you manage to recognize when a function is odd in sign or not, it's going to be helpful. Sorry again. The idea is the following. It is related with the parity of the exponent sometimes, but be careful. I cannot say yes because it's not true. Okay, in this case, it's a product of two trigonometric functions. The exponent is going to make you know if this is odd in sine, odd in cosine, or even in sine and cosine. In this case, you can just apply many changes. We are going to focus on one. We are going to consider that the function is odd in sine, so the change is cosine of x equals t. Okay, so let's see what happened. There are many other ways, again, many other changes. And the problem is that the integral you obtain at the end maybe is not so easy. Okay, so if we focus on this change, cosine of x equals t, then sine of x becomes 1 minus t squared. You can ask me, where did this come from? Where is 1 minus t squared coming from? Okay, piece of cake. I only asking you to remember a few trigonometric formulas. One of the most important trigonometric formulas you need to remember is that cosine squared plus sine squared equals 1. This thing is coming from this formula, cosine squared plus sine squared equals 1, okay? So, let's see, how are we going to deal with this? If sine of x equals the square root of 1 minus t squared, then oh no, be careful. Forget what I was saying. The sine of x equals this function. Now, if we solve from this substitution, the x, then x becomes the arc cosine of t. Please remember always that the inverse function of a trigonometric function like sine or cosine is not 1 over sine or 1 over cosine, or sine power minus 1, cosine power minus 1. This is just notation. The inverse function is arc sine or arc cosine, such in this case, like in this case. Okay? So, x is the arc cosine of t. The derivative of the arc cosine is minus 1 over square root of 1 minus t squared differential of t. And you are probably thinking now, should I remember the derivative of the arc cosine? The answer is yes. If you are going to apply this change, yes. But it's not difficult. It's not difficult. Why is this change useful? Is this change useful because this square root is going to be simplified somehow. So, guys, it's not difficult to remember that the derivative of the arcsine or arccosine is going to have exactly this square root on the denominator. When it's arccosine, I have a negative sign here. When it's the arcsine, it's going to be positive. But the derivatives are not difficult to remember. Once I see the expression of sine here, I know the derivative. Okay? So if we apply this substitution, cosine of x is going to be t, sine of x is going to be this square root, and differential of x is going to become this expression, the previous integral becomes this integral. Okay? Sine cube has been changed by a square root of 1 minus t squared, everything cube. Cosine cube has been changed by t cube, and the differential of x has been changed by the expression. Okay, do you see that I can simplify things here? For example, t squared remains the same. This square root on the denominator is going to simplify with one of the numerators. I have 3 square roots on the numerator, so 1 disappears, leaving this square root power squared. Oh, but square root power squared, it makes the cancel each other, so the square and the square root disappears. So the only thing left is 1 minus t squared. This negative has been written outside, so I just cut this. How do we solve it? Let's multiply. T cubed times 1 is t cubed. T cubed times t squared is t to the 5th power. I still have a negative outside, so I'm going to put it inside and change the order of whatever is inside. So I got this. This integral is trivial, guys. The integral of t cubed is 1 over 6t to the 6th power, and t cubed is 1 over 4t to the 4th power. Okay, we add 1 to the exponent and divide by this same number, plus a constant. Oh, but by the way, you apply this change at the first stage. So I'm going to change t by cosine of x. And the remaining solution is that one, once you replace by the t by cosine of x. And c is the constant of integration. So as you can see, it's not difficult. Yeah, probably you are thinking, yeah, but you just apply a lot of properties, a lot of things during the process. Yes, I did. Not so difficult. But as you can see, integrals are not as easy as derivatives. We have to work with many mathematical properties. Okay, guys, what have we seen today? We have seen an example of a trigonometric integral that is odd in sign. And we have seen how to solve it with the change of this type of integrals. I hope you find this helpful, and thank you for your attention.